Hi audience and student, now we begin the second topic of this lecture series. In this topic, we study the circuit component employed in the power stage of PWM converters such as semiconductor switches and energy storage or energy transfer devices. We'll focus on the fundamental behaviors of the component along with their circuit equations in PWM power conversion circuits, the physical structure and operational principle of the component are only briefly discussed. For your information, the content of this topic number 2 are taken from the chapter 2 of this book. Topic number 2 first deals with power semiconductors, including MOSFET, Diode, and more importantly, the SPDT switch implemented with the MOSFET Diode pair. Some details about the SPDT switch will be explained in the next slide. Second part of this topic covers the energy storage and transfer device, inductors, capacitors, and transformers. The first lecture of this topic, the lecture 1, discusses the semiconductor switches as the power stage component. First, we'll discuss the structure of MOSFET along with its switching characteristics, and we'll cover the diode and the switching characteristics of the diode. We also discuss the structure of diode briefly, and finally we'll discuss the MOSFET diode pair as an SPDT switch. The schematic of this SPDT switch is something like this. There is a MOSFET switch first. MOSFET switch is located here, and this is N-channel MOSFET, and the MOSFET switch is followed by diode. Diode is here. So we have 3 terminals, and this terminal is denoted as A terminal, where the active switch is connected, and this is denoted as P terminal, where the passive switches are located, and this C terminal is the place where this active switch, this active switch and passive switch merge together, and the symbolic notation of this SPDT switch is this one. This is the A through, and this is the P through, and there is one pole at C port. This is the pole. This is pole, and this pole is connected either A or P throws. Okay, so this pole is always connected either A through or P through, and this SPDT switch is playing the most important role in the PWM power conversion, as will be demonstrated in the later slides. Next slide will show the structure and basic operation of MOSFET switches. One is diagram used in electronics book. Okay, the structure of power MOSFET is different from this. Okay, we'll be discussing that in later slide, but just use this planar structure. So P is body, and this is strongly doped N region, and this is called drain and source. They can invert it in general, but that is not true for the power switches, power MOSFET. You don't want to invert them. So, and this is silicon oxide layer, is insulator, dielectric material, actually very good dielectric material SiO2. All right. So this is planar structure, and this is source, drain, gate. This is a symbol, source, drain, gate, and this is the voltage between gate and the source. This becomes positive and negative. Okay, you remember this arrow and everything. Okay, when this gate voltage is 0, VGS is 0, or negative, or smaller than some value called threshold voltage. So VTH is lower than some value, threshold voltage, typically 2 or 3 volt. Then there is no channel. This is isolated. That means you have PN junction in this direction. Another PN junction here in this direction. Okay. For this directional current, this diode is reverse biased, so it is impossible to carry current. Same is true here. So they are isolated. Okay. So VTH is called the threshold voltage. So when this voltage between gate and the source is smaller than this, is just turned off, open circuit. It behaves as open circuit. Okay. If this voltage is increased beyond the threshold voltage, then this positive charge is here. This positive charge will attract these electrons from this N-dominant region. So it creates a channel. Now this current is passing through this way. Also, it can pass through this. So basically, this is bidirectional switch. Okay, but later on we'll be using this device as a unidirectional switch. Okay, so when this gate source job is larger than threshold voltage, this RDS on is very small. So typically tens of milliohms. So it behaves as a short circuit. Short circuit. Okay, shown here is structure of practical power MOSFET. This structure is different from the previous one. Okay, so it consists of, you are seeing just a part of it. This part is repeated forever. Like 1,000 of this is all connected together in parallel. Okay, okay. So this is just part of cells out of this large collection of this planar structure. It's in this direction. It's a planar structure. But if you see this part, this is the vertical structure. All right. So there is a. This is the metal contact. Oh, I forgot mentioning that. This is the metal contact. This part is metal contact. Like aluminum, this is metal. And metal part is this one, metal contact here. And this is the metal contact, okay? And there is a plate here. So entire plate here is drain, and this is source. They are connected together. So if you take a look at this part only, this is a source and this is drain. This is the gate. All right. With positive source, plus, it has positive source. This positive source will attract the electrons here, and create channel, short channel here. But this part is both. So this is the N and this is the on. So there is a current path create from this drain to this source. Okay, two sources are connected in parallel. So this whole part is drain and this one connected together is source, and gate is here. This is SiO2 and this metal contact. If positive voltage is applied here, the channel is created. Okay. Difference between this structure and the previous structure is channel has this vertical structure, right? So channel is thick, very thick. That means this device can carry the larger current compared to the previous structure, and it has many of this repeated here, thousands of them, so it can carry large current, right? And this area has this N-P region, okay? So this works as a depletion region during the operation. So this can sustain a large current. So drain VDS, drain source voltage, can be increased with this thickness of this device, okay? So to increase the current capacity, the device should be thick. And to increase the voltage structure, voltage threshold, it has tall structure. Okay, so for high voltage structure, this should be increased. For high current device, this can be widened, should be widened like this. Okay, so this is the basic structure. But important thing is here we have NPN structure. So this is what? BJT, directional BJT, right? And this device will be used as a switching device, okay? Then there is a capacitor between this gate and the source. There is some capacitor consists of this dielectric capacitor and the junction capacitor, right? So for this device, the current will be flow I, okay, let me use this notation. IP minus N plus. So that current is this one, this current, right? So this current will turn on this junction, okay? Because the current here, this parasitic current is, there is some effective capacitance, some of dielectric capacitance and junction capacitance, and this is the basic equation, VDS divided by dt, okay? So high-speed switching, so this will be very large, all right? For the fast switching device, this time derivative of this voltage will be large. Then this voltage will be very large. Then that current will be large. That current will turn on, and this diode will turn on. Then this device is not a MOSFET anymore. It's some strange device that should be avoided. Okay. Otherwise, it's not working properly. It's not working as intended. So to avoid that situation, there is just some structure. All right. So this is the problem. To avoid the problem, people create circle here. So this was previously it was fully filled with N plus material. They take out some part, and this is the P minus. Okay. So there is a connection P minus, and this is the PN. No, resistance of this will be very, very small. this is reverse bias. So resistance will be very large, okay? But with this, the internal resistance will be very small, okay? So this, with this, I'm missing something, okay? But not important, okay? The conclusion is important. To avoid accidental turn on of this parasitic BJT, they create this, and that avoid the turn on of this, okay? So to avoid turn on, they create this hole. So if you look at this structure from the top, okay, this is the side view. This assumed we cut here, but you look down from the top, then it looks like some donut shape. It will be something like this. Okay, so there is a diode here. P-N is diode. So if the potential of this is higher than this one, this will be turned on. Okay, this is called body diode. It's called anti-parallel. Anti-parallel means direction of the main current, and the direction of the diode current, they're opposite. So it's called anti-parallel body diode. Okay, so it has diode, built-in diode. If you have MOSFET, power MOSFET, there is diode. Okay, you should consider them all together. So we have a symbol of diode, MOSFET here. Okay, this is flipped vertically. So we have this gate and the source and the drain, and it has this anti-parallel body diode. If this is turned on, so main current is coming from the drain to source. If diode is turned on, that current goes to opposite direction. So it's called anti-parallel body diode. Okay. But in most cases, for the PWM converter, for the basic PWM converter, like buck converter, boost converter, buck boost converter, this voltage is always higher than this voltage because of this voltage source. Right? So in general, automatically this diode is reverse biased. So you don't have to worry about this. So you ignore this, right? You ignore this. But when you drawing the circuit diagram, it's better to draw this body diode here too. Okay? So for the conventional applications, the diode is always reverse biased. So it's not doing anything. You just ignore it. Okay? But they use in circuit diagram, they use that diode. So long time ago, my student, some of not so smart student, my student, they bought this. They bought separate diode, and they connect like this. Okay. So you don't do that. Okay. It's internal device. Okay. So we are not using this, but this diode can be very useful for the what? Resonant power converter. In resonant power converter or bidirectional power applications, in PWM converter for bidirectional applications, we use this as active device, functional device. So it comes for free for that case. Okay, otherwise you just ignore this, right? But this diode is very slow diode. This is the parasitic device. You don't have any additional effort to improve the characteristics of this. So this is very large diode, but that is okay for the resonant converter and bidirectional power applications. Right? And switching of this diode is very simple. All right. So you are actively controlling status of this. When this VGS is larger than this value, maybe 15 volt, device is turned on, then drain source is just, you're assuming this RDS on time resistance between drain and source is assumed negligible, shorted, opened, shorted, on, off, very easy, okay? Right? Graduate student, they think diode is very easy to understand because there are only two terminals, they have two status. That's not true anymore. Right? MOSFET is very easy because we know when MOSFET is turned on, turned off, because we are controlling on-off status of this device. But diode is different. Diode status is determined by not you, but by what? Circuit operation. So you should understand the entire circuit operation to judge the status of the diode. Okay? So that is sometimes that is very tricky. Right? Okay, repeat this slide. This is the symbol of N-channel MOSFET as drain, gate, and source. And there is a body diode, anti-parallel body diode. And usually for the conventional PWM applications, there is a large voltage connected here. So this becomes plus, and this is negative. So this is always reverse biased. So the body diode is not doing anything here. But some case, there are some applications, this becomes positive and this becomes negative. So actually one student asked the situation about that. So I was thinking about that. So I'd like to give my answer. All right. Suppose this is the positive and this is negative. The current will through this. Okay. And this is diode. The diode is not conducting any current until this voltage becomes 0.8, 0.7. Okay. So there is a fixed resistance RDS on, and the current starts flow this direction. When this voltage drop across the channel resistance exceed 0.7, then this will be turned on. Then the extra current, larger current, I think will flow through this diode because this voltage is fixed. So initially the current goes to this and turns on diode, and later on large current will go through like this. That is the story. I don't know that is the correct in theory, but that is my assumption. Okay. So anyway, partially the current flows through channel, and the main current will flow through this body diode. All right. So and about diode, okay, passive switch is typically is diode. So this is a symbol of diode. So diode is PN junction. Okay, the P part becomes anode, and N part becomes cathode. And this is the symbol of anode A, and you are using letter K, not C, for cathode. Okay, and this is the curve, 3D ID curve of diode. But you should think about this situation. This is the situation, how the current, device current is generated. There is a diode. Diode connected like this, and there is a resistor and the voltage source here, whose magnitude and directions can be changed. Okay, when polarity is like this, diode current will flow ID this direction, and the voltage across the diode is defined like this, VD, and you are increasing the value of this current source, the voltage source, and you are measuring VD and ID. The plot is here. This is the exponential curve. Okay. Now you swap this polarity of this, then there is no current, and all of a sudden, huge current start to flow. This when this time breakdown occurs. Okay. So this is the real curve, exponential curve, and some strange curve. Okay. So this is a nonlinear curve. So we try to simplify this. So we make this approximation up to this point. We replace this exponential curve with this straight line and another straight line, and we forget about this part. So we are trying to approximate this nonlinear curve with this piecewise linear curve. There's a connection of piecewise linear curves. So it's called piecewise linear approximation. Piecewise approximation. There is a final slope, okay? But this RD is very small. If RD approach 0, it becomes the vertical line like this, okay? And this VDF is also small. So if VD reduced to 0, this curve looks like this, and this is the ideal diode curve. Very, very difficult to understand without this. So when you think about this curve, you should think about this circuit. So this is the measured curve. You are trying to approximate this nonlinear curve with piecewise linear function like this. Okay, and this region, this operational region, we call it on state. So in on state, we have one DC voltage source and one resistor here, and ideal diode. Ideal diode is shown when voltage here is larger than voltage at this terminal, but it carries current only one directional from anode to cathode. Okay. Ideally, this becomes very small, so VDF becomes very small, and the RD, on time resistance, becomes very small. Then you can replace this with short circuit. Okay, so this is the status of this diode when turned on, and when turned off, this operational area, not this one. This is breakdown region here, so there is no current at all. So it looks like open circuit. So when diode is turned on, it becomes short circuit, and when turned off, it becomes open circuit, and this value VDF and RD are assumed 0 for the ideal discussions. Okay, and the status of diode is determined by condition of application circuit. Right. So you are not controlling this. This status is determined by operational condition. For example, there are two ways of controlling the status of diode, or there are two ways of interpreting the state of the diode. So first, you can think about the voltage. So it's called voltage controlled switching. Diode is turned on when external circuit impose the potential, which is this part is higher than this part, then diode becomes turned on. Okay. Otherwise, diode is turned off. There are only two possible status. One is on, one is off. Okay. So when you think about voltage, if this voltage is higher than this, diode is turned on. All right. The other way is determining the status of diode using diode, the current. if external circuit impose a positive current from anode to cathode, diode is turned on. Okay, when this external circuit impose this current flow this direction, suppose the external circuit is pushing current from here to there, then diode is turned off. It's called current controlled turn off. Okay, so knowing the on and off state of diode is very important, and this helps to understand the status of diode. This is an example. Okay, so this is one example, and this is another example. Here is a diode. This is practical diode, but we may assume this is the ideal diode, and there is a voltage source, and voltage source can be varied in the polarity and in the magnitude. So initially, this voltage is, this one is negative, positive, so it has this minus 2 volt. Then voltage here is negative, this part becomes negative, positive, that means this external circuit imposes negative voltage across the diode, and diode is turned off. So diode is turned off here, diode is off. Then no current is flowing through this. This is open. Then voltage across diode is this voltage plus this voltage, which is 0. There is no current, so there is no voltage drop. So this whole voltage appears across this diode, which is this. Okay, and suppose this negative voltage is increasing like this, so it moves toward 0 and the positive direction. At this moment, when this voltage passes 0, then diode is turned on. Okay, so this diode is turned on by this voltage source. When diode is turned on, it's short circuit, and current is flowing this direction, and this whole voltage is applied across this resistor. Okay, so if you draw the voltage waveforms for this state, when diode is turned off, this Vs is entirely appears here. When diode is turned on, Vd is 0. So this is the voltage across this diode. So when diode is turned on, voltage across diode is 0. This is ideal diode. So you showed it, and whatever voltage occurs here appears here. So this is the voltage across this resistance. So Vd, Vr. Okay. So this is Vs, and this is the Vd and Vr. So sum of Vd and Vr, which one is this? Sum of this becomes the Vs. Is something similar to KVL, Kirchhoff's voltage law. Is not this one. Is something else, but the concept-wise, this is very similar to the KVL. Okay, since the entire this Vs is voltage here plus voltage there, which is this. Right. So this is the situation where this diode is turned on and off by voltage source. You may feel this is the artificial, something imaginary, but in real application, this situation occurs frequently in real circuit. The diode is somehow reverse biased some volt, and that the voltage will be reduced by some reason, and when voltage reduced to 0, diode will be turned on. Okay. Similar situation is explained here. This is a current source, and this is the ideal diode, and in parallel with this resistor. So Is is pushing this current, then this current will turn on diode. Then this is the shorted, then entire current will go through this. There's no current, 0 current, but there is some finite current. There is no current for diode to go through this hard direction. So all current goes like this. So current is shown here. It starts from this positive value and reduces in value. When it passes 0, this is turned off, right? Because the current through this diode is somehow reduced to 0, then diode is turned off, then current divert from this direction to this direction. So this is the IR. Okay? So when diode is on, this current is the same as this diode current, and when diode turned off, this current is the same as current through resistance. And in the similar way of the previous case, this ID plus IR always becomes IS, which is very similar to KCL, Kirchhoff's current law. Okay, in some sense. Okay, so this happens a lot. Okay, in many applications, the current through diode will be reduced by some reason due to the operation of other circuit. Then current will be reduced like this. Then diode turns off. Okay, and this current should follow the other way around. It's called the freewheeling path. Okay, so we'll discuss freewheeling path later. Okay, so we discussed the MOSFET and diode. As I said many times, the MOSFET diode functions as a SPDT switch, as a pair. They come together and works as one switch, SPDT switch. This shows that concept. Okay, or SPDT switch. We used this symbol to understand the operation of the PWM converter. Then this is implemented, this pair of MOSFET and diode. Okay, so this is the SPDT switch, and this is the switch drive signal. Means for the time period A, switch is connected to the terminal A, and for the time period P, switch is connected to P. All right. So then this is replaced by two switches. So one switch is here, another switch is here. This is turned on, connected. So this switch, this pole is connected to through A, like this, and this is turned off. This is when this pole is at A position, and when this pole is at P position, this switch is turned off, is opened and closed, like this. Okay, so this is the same thing, same functional diagram. Okay, and this shows how to implement this SPDT switch with this a pair of MOSFET and diode. Okay, very simple. When MOSFET is turned on by this gate drive signal, VGS is larger than this threshold voltage during this period, on time period. Then this is turned on. Then this diode is reverse biased by this voltage, so turned off, which is this, right? Then this current is passing through this diode. Okay, so now this switch is opened. Then this current turns on this. Okay, as I said, when this positive current is pushed from the external circuit, diode is turned on. So this is turned on, then current will flow this. That situation is the same as this. Okay, so this is the implementation of this SPDT switch using this MOSFET and diode pair. So in all applications, in all the converters and practical application, you will see this. At this, there is a one pair or two pairs or more pairs of this MOSFET and the diode should be in the circuit. and they should work as SPDT switch. Otherwise, the converter is not working, or application circuit won't work. Okay, so that is the basic idea. So MOSFET, when MOSFET is turned on, diode is turned off by this reverse voltage. It's called voltage controlled turn off. When MOSFET is turned off, this diode is turned on. It's called current controlled turned on. Okay, so diode is turned off by this voltage source, turned on by this current source. Right? If you take a look at this diagram, we connect this voltage source and the current source in between this SPDT switch in this manner. This is the only possible configuration. There are improper, incompatible, or unworkable connection of SPDT switches. Okay. For example, think about this. There is a SPDT switch, and you connect two voltage sources here and another voltage source here. You connect one current source, another current source, and you connect one current source, voltage source. So all of this circuit is not workable because of some problem. So for this case, think about the case where the switch is A position. This pole is located at position A. Then there is a problem. If this magnitude of this voltage is identically same as this one, that is okay. If there is any finite difference between them, you are violating what? KVL, right? So KVL will be violated, so this circuit is not working. It will be shorted. KVL violation. There is a problem, so it won't work. If this pole is connected to here, you are shorting this voltage source, which is a big problem. So at P position, you are actually shorting source. Okay, so it's not compatible, incompatible, unworkable, unoperational. So this won't work, right? Think about this one, this second configuration. When this pole is at A position, the magnitude of this current and the magnitude of this current, if they are identically the same, that's okay. Otherwise, you have KCL problem. KCL problem will be violated. When this pole is at P position, this one might be okay. This is okay, okay? But this current source is opened, okay? So you should have a pulse to maintain this current flow. So current source is opened. That is also a problem. So it's not working. How about this one? If this is connected like this, that is fine. Okay? So this is a current source and this is a voltage source. They are connected in series. Okay? So voltage source is generating a fixed voltage regardless of the current passing through this. So there is no problem. Okay, this current source is pushing current out of this regardless of value of voltage across this. So there is no problem, but this has problem. Okay, when this pole is connected to A, this one is okay. When this pole is connected to the P, then you are shorting the voltage source. And also opening this current source. So we are in double trouble. Okay? Right. So this is one possible connection, operational connection of SPDT switch. Okay. But there are some different from here. This is one example. This is another example. And this diode is connected here, and the switch is here. Okay. They look different, but it also works as a SPDT switch. And for this configuration, this MOSFET is here, and diode is the other side of transformer. So it looks different from the previous example, but functionally they are same thing. Suppose this switch is connected, then this voltage will reverse bias this diode. So diode is turned off. Okay. Then there is an inductor. As you will see later, I'll explain this soon. Then this inductor will develop a current through this. So current is flowing through this, and switch is turned off. That current should maintain continuity of its flow. Then current that was flowing through this coil will turn on this diode. So here Q is on. Then means diode is off, Q is off, D is on. This is the operation of SPDT switch. Okay, this is one example. It looks different from the previous case, but the functional behavior of two switches are exactly same. When one switch is turned on, the other one automatically turns off, and vice versa. Okay. Here we have a transformer. Okay, we'll discuss this later. So I assume every student is start learning this one. Maybe you already familiar with this. Okay, but just assume you are seeing this for the first time. Okay, then when this switch is turned on, there is inductance. Always this practical transformer has inductance across its terminal. It's called magnetized inductance. We'll be discussing this later. So there should be a LM. Okay, magnetized inductance is here. So this is turned on. Then voltage, plus minus voltage will be applied here. And this is because of this notation of the dot, plus minus voltage will across here. And assume the initial voltage of this capacitor is 0. So this capacitor is shorted. Then diode is reverse biased. Diode is turned off. So Q is turned on. When Q is on, diode is off. Okay, so there is no current because the diode turned off. Then there is no current either here because of this ideal transformer property. Okay, then there is a current flow like this, and this current will be increased. in some shape, okay? Then this is turned off, then this current should maintain continuity. Then this current will circulate this. Then some current is coming out of this dot terminal. Some current will come into this dot terminal. So it should go in like this. Then diode is turned on. So in short, when Q is turned off, diode is on. So they are separated, this MOSFET and diode. They are separated by this transformer. Still, they are combined functionally, and they work as SPDT switch. So of course, this circuit is okay. It works properly. So all the operational circuit or converter should have SPDT switch in it. Okay. Otherwise, the circuit is not working. Won't work.